Hello. Now let us start squarable potential. We have seen that infinite squarable potential. Now we will see finite squarable potential. So now topic is finite square well potential. For this you may go through previous video. In this case again we have two cases. First one is when energy of the incident particle is greater than potential height, and second when energy of the particle is lesser than potential height, or more clearly it will be greater than 0 and less than V naught. So first, for E greater than V naught, what we see is squarable potential looks like this, and here we have x direction Vx, taking here center 0 as we are discussing for symmetric finite squarable potential. So here taking a by 2 and here taking minus a by 2. It means that we are taking potential of the form Vx is equal to V naught 0 and V naught. V naught for x less than minus a by 2, 0 for minus a by 2 to x to a by 2, and again V naught for x greater than a by 2. So this height is V naught. This height is also V naught, and here V is 0, and we are treating with incident particle whose energy is E. So since considering about first case, so drawing energy level of the particle which is higher than potential height. This is E, energy particle higher, potential lesser, condition first, and on 0 this is taking axis for potential, so writing Vx, Now, when particle incident from left side, so for moving particle we have wave packet according to de Broglie concept. It means that we can write wave equations for such motion. So writing for incidence, this is a e to the power I k1x, for reflected b e to the power minus I k1x, for transmitted c e to the power I k2x, for again reflected d e to the power minus I k2x, for again transmission e to the power I k1x. Why k1? Because we have the value of k1 is equal to under root 2m e, and value of k2, this is upon h also 2m e minus v naught upon h cut. Okay, so as we know that we have read about potential step, also potential barrier. As we have solved for potential step and potential barrier in previous video, in similar way we can solve for this condition. So this is easy much, and you will find shortly reflection coefficient. It means that classically this particle will move from first region, this is region first, this is region second, and this is region third. So particle will move from first region to second region. So main question is that will this particle reflect also? So answer is yes, but classically answer is no. So this is main differentiation, main difference in case of classical and quantum view. So using these videos you can easily calculate for reflection coefficient for this potential, for this condition. So no problem. Now we are going to deal with second case, that is bound state solutions. Let us start bound state solution, that is for case second. So case second of finite square wave potential, this is E less than V naught, and obviously this is greater than 0 also. Greater than 0, lesser than V naught, and this is bound state. So drawing figure for that. Forming square well potential, this is x-axis, here Vx at or 0 same a by 2 minus a by 2, but here energy of the particle is lesser than V naught. So drawing value region of E is below V naught. So this is E while this is V naught and this is E. Obviously energy of the particle is lesser than potential height. So here also this is V naught, and we know that for symmetric potential format is Vx is equal to V naught 0 and V naught. V naught for x less than minus a by 2, 0 for x minus a by 2 to a by 2, and V naught for greater than a by 2. So this is Vx and this is symmetric potential. Now classically when E is less than V naught, then this particle will bounce back. In this region, because when energy is lesser it will move here, but after moving here, now this height is greater and this energy is lesser, so this particle will not cross this region, and again when this will come here, energy is E but height is V naught, it will again not cross this region also. It means that classically the particle will move only in this region, that is in this region, minus a by 2 to a by 2, and reflected at a by 2 and minus a by 2. So this is classical statement. Now according to quantum view, this is expected that we will get here a discrete energy spectrum. And one more thing, that wave functions in this region here and here decay but oscillate in this region. So for this, writing plane wave equations so that we can write e to the power k1x, as we told that in this region and this region it decay but oscillate in this region. So wave function will be as, and for this minus k1x, but for this will be b cos k2x and c sin k2x. Why this is? For symmetric or asymmetric, that is even or odd. Okay, so writing Schrodinger wave equations for these three regions: region first, region second, and region third. So for region first, dy square psi 1 upon dy x square plus 2m e minus v naught upon h cut square psi 1 is equal to 0. As v naught is greater, so we will write this as del square psi 1 upon del x square, you are writing here, del square psi 1 upon del x square minus 2m v naught minus c upon h cut square psi 1 is equal to 0, writing this k square. K1 square psi 1 is equal to 0, and solution of this will be 1, and if you will take antisymmetric, then this and this, and for symmetric, this and this and this. So for this will be psi 1 is equal to a e to the power k1x. Okay, now writing for this is for now for second region. For second region, del square psi 2 upon del x square plus 2m e minus v naught, but v naught is 0, that is v is 0, so only e upon h cut square psi 2 is equal to 0, writing k2 square for this one. So del square x2 upon del x square plus k2 square psi 2 is equal to 0. So psi 2 is c sin k2x for antisymmetric. Or we can write c cos k2x, this is we have taken is c and this is b cos k2x, this is for symmetric, because in bound state there is theorem that wave function may be symmetric or antisymmetric. So in this bound state, wave function may be symmetric or antisymmetric, so we will take both. Now writing for region third. For region third, del square psi 3 upon del x square plus 2m e minus v naught upon h cut square psi 3 is equal to 0. Since v naught greater than e, so writing in this manner, del square psi 3 upon del x square minus 2m v naught minus c upon h cut square psi 3 is equal to 0. Now writing this quantity as, again this is k1, so del square psi 3 upon del x square minus k1 square psi 3 is equal to 0, and solution will be psi 3f is equal to d e to the power minus k2x. So we get wave function as we have told that according to theorem, in bound state eigenfunctions are symmetric or antisymmetric. So we have antisymmetric wave function we can write eigenfunction also. This is what psi ax a e to the power I k1x c sine k2x and d e to the power minus k1x. This is for this reason. This is minus a by 2 to a by 2, and this is for greater than a by 2. Also symmetric eigenfunction. Symmetric eigenfunctions are, we will write psi sx, this is equal to a e to the power I k1x b cos k2x d e to the power minus k1x. This is for minus a by 2, this is for minus a by 2 to a by 2, and this is for greater than a by 2. So we have antisymmetric wave function and also symmetric. Now we have to find eigenvalues. As we know that in bound state we have discrete energy level. So to find that energy level, we will apply continuity condition, boundary condition. Now applying continuity condition, that wave function is continuous with respect to x, that is at boundary minus a by 2 and plus a by 2. So as we know that, consider this psi 1 psi 2. So these are continuous at x is equal to minus a by 2, and this is continuous at x is equal to a by 2. As same here, this is continuous at x is equal to minus a by 2, and this is continuous at x is equal to a by 2. So we will apply this condition. So using continuity conditions, and offer this is log derivative. So continuity condition, this is of log derivatives. So writing 1 upon psi x deva psi a x upon deva x. This is of psi a, and x is equal to plus minus a by 2. And also for symmetric, 1 upon psi sx deva psi sx upon deva x. This is also at x is equal to plus minus a by 2. This is for antisymmetric, this is for symmetric. So we will equate these two, first second, at boundary of minus a by 2 and at boundary a by 2 we will evaluate for this. So doing for this, first suppose this is psi a1, this is psi a2, and this is psi a3, and here this is psi s1, psi s2 and psi s3. So that using for antisymmetry we can write condition. Condition will be 1 upon psi a1 x deva psi a1x upon deva x is equal to, and also of this one, 1 upon psi a2x deva psi a2x upon deva x. So use this relation for x is equal to minus a by 2 and x is equal to minus a by 2, this relation. So what we get, 1 upon psi a1 x, that is this one, 1 upon a to the power I k1x this is not I, only k1x. Okay. So for this also taking derivatives, so deva by deva x of this, what will be k1 and a to the power k1x. We have calculated from here derivative of dy dx of this part is equal to 1 upon psi a2, that is this one, 1 upon c sine k2x, and differentiating this also. So this will be k2 c cos k2x. So this will cancel out, this is cancel out, and this will become cot. This is at x is equal to a by 2. So we will write here k1 is equal to and this is cot k2 x, this is at x is equal to minus a by 2. So when you will put a by 2 minus a by 2, this will become minus, and this is plus, So writing in better manner, cos k2 a by 2, since cos minus theta is equal to cos theta, but this will be sin k2 a by 2, sin minus theta is minus sin theta, so this will be minus here, and k2 also. Now this will become cot. So k1 minus, shift minus here, cot k2 a by 2 with multiplication of k2. So this is, and when you will try for psi a2 and psi a3, same you will get. Now we will use for symmetric condition. So for symmetric, writing condition 1 upon psi s1x deva psi s1x upon deva x is equal to 1 upon psi s2x deva psi s2x upon deva x. This is at x is equal to, yes, a by 2, or you may take for minus a by 2. Yes, for minus a by 2 we will take this, and for a by 2 we will consider s2 and s3. Okay, so here this is minus a by 2. Now putting value, so psi s1x here, so writing 1 upon a to the power k1x and differentiating this part, so k1 a to the power k1x. Now taking second, b cos k2x, and after we will take, yes, its derivative, that will be k2 minus sin k2x, and these are at x is equal to a by 2. We will put, this will be cancelled out, shift this minus here, so minus k1 is equal to, now look, here is k2 sin k2x, this will be sin k2 minus a by 2, so minus will be outside due to sin minus theta is equal to minus sin theta, and upon cos k2 a by 2. A by 2, and this minus minus cancel out, so this will become tan. So what we get, k1 is equal to k2 tan k2 a by 2. So we have got this relation and this relation. Now we will shift this relation into another form of equation, because these are, we cannot solve directly this, so we will use graphical method to solve these equations. Yes, this one and this one also, we will use graphical method to solve these equations.